You begin in stillness. Imagine yourself lying beneath a sky so wide it seems to have no edge. The air is cool. The world is quiet. Above you, stars shimmer softly, patient and ancient. They appear fixed, like tiny pinpricks in a dark curtain. But you are about to discover that nothing in this vastness is truly still. For a long time, humans believed space was emptiness, a silent stage where planets drift and stars burn. It felt like a backdrop, unmoving and indifferent. But slowly, gently, science revealed something far more intimate. Space is not empty. It is not rigid. It is not silent. Space is a fabric. Not fabric you can touch with your hands, but fabric in the way a woven sheet holds its shape while still able to bend. This fabric is called spacetime. It is the union of space, the three dimensions you move through, and time, the steady rhythm that carries you from one breath to the next. They are not separate threads. They are woven together. And as you rest beneath the night sky, you are resting within that fabric. Now imagine placing a heavy stone onto a stretched sheet. The sheet dips under the stone's weight. If you roll a small marble nearby, it does not travel in a straight line. It curves inward, drawn not by an invisible tugging force, but by the slope beneath it. This is gravity. It is not a rope pulling objects together. It is the bending of spacetime itself. Massive objects, stars, planets, galaxies, press into the fabric. They reshape it. And everything else moves along the curves that form. You feel gravity every moment. Your body rests against the Earth because our planet bends spacetime around it. The Moon orbits Earth because it travels along a curve carved into the cosmic fabric. Earth orbits the Sun for the same reason. You are not being pulled. You are following a path shaped by curvature. Let that idea settle gently. Gravity is geometry. Motion is guided by shape. Now imagine something more dynamic. Picture two heavy stones resting on that stretched sheet. If they begin to move, circling one another, the fabric does not remain calm. It shivers. Ripples spread outward across its surface. In the real universe, when massive objects accelerate, when they orbit, collide, or explode, they disturb spacetime. The fabric trembles. Waves travel outward at the speed of light. These are gravitational waves. They are not waves of light. Not waves of sound. They are waves of space itself. As they pass, they stretch distances in one direction and squeeze them in another, ever so slightly. If one were to move through your body right now, you would not feel it. The effect is unimaginably small. Smaller than the width of a single atom compared to the size of Earth. And yet, they are real. For a century, they were only a prediction, an elegant consequence of Albert Einstein's equations in 1915. His theory of general relativity described gravity not as a force, but as curvature. And hidden within those equations was the possibility that spacetime could ripple. Einstein himself doubted whether such waves would ever be detected. They seemed too faint, too subtle. The universe would tremble, yes, but who could possibly notice? As you lie beneath the imagined stars, consider how extraordinary this is. The cosmos is not silent stone. It is responsive. It can quiver. It can ring. When a massive star collapses. When two neutron stars collide. When black holes spiral together in darkness. The fabric stirs. These ripples do not fade quickly. They travel across billions of light years, carrying information about their origin. They move through galaxies, through clouds of gas and dust, through planets and people. Through you. Right now, countless gravitational waves are passing through your body, unnoticed. They stretch you by less than a fraction of a proton's width, then release you. Stretch. Release. Stretch. Release. So gently that no nerve can sense it. You are floating in a sea of subtle tremors. Pause there. Feel how this idea shifts your sense of the universe. The night sky is no longer a silent painting. It is an ocean. Deep, dark, and alive with motion. Every massive event sends ripples across its surface. And yet, for most of human history, we could only see the universe through light. Telescopes captured starlight. Radio dishes gathered radio waves. X-ray observatories sensed high-energy flares. All of it light in different forms. But gravitational waves are different. They are not blocked by dust. They are not scattered by matter. They pass through almost everything untouched. They carry stories that light cannot tell, stories from places light cannot escape. Imagine two black holes colliding in total darkness. No light escapes their grip. No glow announces their merger. To traditional telescopes, the event is invisible. But spacetime knows. It trembles. And that trembling travels outward, whispering of what occurred. The universe, it turns out, is not only something you can see. It is something you can feel if you learn how to listen carefully enough. For a long time, humanity did not have ears sensitive enough to detect these ripples. The waves that reached Earth were too delicate, their distortions too small. Measuring them would require extraordinary patience, precision, and ingenuity. But the idea remained, like a quiet promise. If spacetime can bend, it can vibrate. If it can vibrate, it can carry echoes. If it carries echoes, then somewhere in the vastness, something is ringing. You return to the image of the stretched sheet. A ripple crosses its surface, spreading outward in perfect circles. The sheet settles again into stillness, but the disturbance has traveled far beyond where it began. In the real cosmos, those ripples never truly stop. They move outward indefinitely, thinning but persistent. They are messengers without voices, vibrations without sound. You rest in that knowledge now. The ground beneath you is not rigid certainty. It is curved geometry. The sky above you is not silent emptiness. It is a field capable of trembling. And somewhere, unimaginably far away, two massive objects are spiraling closer together. Their orbit tightens. Their speed increases. The fabric between them strains. The tremble grows stronger. You cannot see them yet. You do not know their shape or origin. But the ripple has begun its journey. You begin by letting the fabric return to your mind. Not cloth beneath your fingers, but something subtler, the invisible structure that holds everything. In the quiet of your imagination, you see it again, a vast, flexible tapestry stretching beyond sight. This is space-time. It does not hang in a room. It is the room. It is the stage and the story and the rhythm of change. You rest inside it now. Albert Einstein once realized something profound, that space and time are not separate actors. They are threads woven together. Before him, space was thought of as a fixed arena, and time as a steady ticking clock, universal and the same for everyone. But Einstein saw that the clock and the stage influence each other. They bend. They stretch. They respond. Imagine again the stretched sheet. When nothing rests upon it, it lies smooth and calm. Lay a heavy sphere in its center, and the sheet dips. Roll a smaller sphere nearby, and it curves inward, following the slope. This image is gentle, but it hides something astonishing. The sheet does not only represent space. It also represents time. When a massive object presses into spacetime, it changes distances, yes, but it also changes duration. Clocks near massive objects tick more slowly. This is not metaphor. It is measurable. It is real. If you could hover near a massive planet, close to its surface, your watch would tick just slightly slower than a watch far away in empty space. The difference is tiny around Earth, but precise instruments can detect it. Satellites orbiting our planet must account for this effect. If they did not, GPS systems would drift and maps would slowly lose their way. Time, you realize, is not absolute. It flows differently depending on where you are. Let that idea soften into you. Time is not a universal river moving at one steady pace. It is more like water flowing over varied terrain. In deep valleys, it pools and slows. On high plateaus, it moves more freely. Mass creates valleys in spacetime, gravitational wells, and within those wells, time runs more slowly. You imagine standing at the edge of such a well. The deeper you descend, the slower time becomes relative to distant observers. To you, everything feels normal. Your heartbeat remains steady. Your thoughts move at their usual pace. But to someone watching from afar, you appear slowed, as though moving through thicker air. This is gravitational time dilation. It sounds technical, but you can feel it as a simple truth. Gravity bends not only space, but the rhythm of moments themselves. Now imagine something heavier than a planet. Heavier than a star. A massive star presses deeply into space-time. Its well is steep. Objects passing nearby curve dramatically. Light itself bends. If a distant star shines behind a massive galaxy, its light may arc around the galaxy's gravity, creating luminous rings and stretched shapes. The galaxy acts like a lens, bending light through curved spacetime. Even light must follow the curves. This is how deeply mass shapes reality. And yet, there is more. When you think of gravity, you may imagine a force pulling downward. But in Einstein's vision, there is no invisible hand tugging objects together. There is only shape. Objects move along the straightest possible paths within curved geometry. In flat space, a straight path is what you expect, a line extending forward. But on a curved surface, the straightest path may appear bent. Think of walking along Earth's surface. If you travel straight ahead without turning, you eventually circle the globe. Your path curves not because you steered, but because the surface itself is curved. So too with planets around the sun. They are not being pulled by a force in the traditional sense. They are following straight paths through curved spacetime. You rest with that image. Motion is surrender to shape. Now let your mind travel deeper. What happens if an object becomes so massive, so compact, that the well it creates in spacetime grows nearly vertical? The slope steepens. The curvature intensifies. Time slows dramatically. Near such an object, seconds stretch compared to distant clocks. Light struggles to climb outward. The geometry grows extreme. These deepest wells are rare, but they exist. To approach one is to approach a place where spacetime bends to its limits. Before we reach that depth, pause to notice something gentle. The bending of spacetime is not violent by default. Around you now, Earth curves spacetime softly. The Sun curves it more strongly. But the curvature allows stable orbits, predictable rhythms, and the steady passage of days. You are cradled in a mild gravitational valley. It is comfortable, familiar, safe. And yet, elsewhere in the cosmos, valleys become chasms. When stars exhaust their nuclear fuel, when the outward pressure of fusion no longer balances gravity's inward curve, collapse begins. The star's own mass draws it inward. The well deepens rapidly. If enough mass gathers into a small enough volume, spacetime bends beyond what seems imaginable. The curvature grows so steep that not even light can climb back out. You feel the edge of that possibility now. A place where time slows toward stillness. A place where space curves inward without escape. A place where geometry becomes destiny. But before you reach that boundary, consider one final thought. Spacetime is not merely a backdrop for events. It is an active participant. It responds to mass and energy. It guides motion. It shapes the ticking of clocks. And when disturbed, it can ripple, as you began to sense in the last chapter. Curvature and vibration are connected. The shape of spacetime determines how it can tremble. Just as a drum's tension determines its tone, the structure of spacetime determines how gravitational waves move through it. To understand the ringing you sensed earlier, you must understand the wells from which those vibrations emerge. And somewhere, in one of the deepest wells ever formed, a massive star is nearing the end of its luminous life, its internal fire fading, its balance failing, preparing to reshape spacetime more dramatically than ever before. You begin with a star. Not a small one like your sun, steady and golden, but a giant, a star many times more massive, burning brighter, living faster. For millions of years it has held itself together through a delicate balance. At its core, hydrogen atoms fuse into helium. That fusion releases energy. The energy pushes outward. Gravity pulls inward. Outward pressure and inward pull exist in quiet agreement. The star shines because of this tension. It glows because it is balanced. You can imagine it as a breath held in perfect stillness. But balance, in the life of a massive star, is temporary. Fusion is a furnace that consumes its own fuel. Over time, hydrogen grows scarce. The star begins fusing heavier elements, helium into carbon, carbon into oxygen, oxygen into silicon. Each stage burns faster than the last. What took millions of years at the beginning now takes mere days. At the very center, iron forms. Iron is different. Fusing iron does not release energy. It consumes it. And so the outward push weakens. The star's internal fire falters. Gravity, patient and relentless, begins to win. You feel the shift. Without enough outward pressure, the star can no longer support its own weight. Gravity pulls the core inward. Collapse begins, sudden, unstoppable. In less than a second, the core compresses dramatically. Protons and electrons are crushed together, forming neutrons. Matter becomes unimaginably dense. The collapse is so violent that the outer layers of the star rebound and explode outward in a supernova, one of the brightest events in the universe. For a moment, the dying star outshines entire galaxies. But at the center, something even stranger is forming. If the remaining core is heavy enough, more than about 3 times the mass of your Sun, even neutron pressure cannot resist gravity. The collapse continues. There is no known force strong enough to stop it. You travel inward in your imagination. Density increases beyond anything familiar. A teaspoon of this matter would weigh billions of tons. Space itself bends more steeply. Time slows relative to distant observers. The core shrinks further. And then, a boundary forms. It is not a surface you can touch. It is not a wall made of material. It is a limit defined by geometry, the event horizon. The event horizon is the point beyond which escape becomes impossible. To leave, something would need to travel faster than light. And nothing can do that. From far away, the newly forming black hole appears dark. Its gravity prevents light from escaping. But the darkness is not empty. It is not a hole in the sense of a tunnel or a void. It is a region of spacetime curved so deeply that all paths lead inward. You imagine standing just outside the event horizon. If you shine a flashlight outward, the beam escapes. But if you step closer still, there comes a point where even light aimed outward curves back inward. The fabric of spacetime is tilted so steeply that all futures point toward the center. Cross that boundary, and return becomes impossible. But here is something gentle and subtle. To an observer watching from far away, you never quite cross the horizon. As you approach it, your clock appears to slow. Your movements become sluggish. Light from you grows redder, stretched by gravity. You seem to freeze near the edge, fading slowly from view. Time dilation becomes extreme. But from your own perspective, you cross the boundary without noticing anything special at that precise moment. No flashing sign marks the crossing. Spacetime feels smooth, continuous. The strangeness lies not in a sudden barrier, but in the geometry itself. Inside, all paths lead inward. At the very center, according to current theory, lies a singularity, a point where density becomes infinite, where the known laws of physics break down. But this word, singularity, is less a description and more a placeholder. It signals the limits of our understanding. It tells you that the equations predict something beyond their own reach. And yet, the black hole is not only an ending, it is also a beginning. When the core collapses, it does not do so silently. The violent acceleration of mass disturbs spacetime profoundly. If the collapse is asymmetric even slightly, it sends ripples outward. Gravitational waves begin their journey. You return to the idea of trembling fabric. The birth of a black hole is not merely the disappearance of a star. It is the reshaping of spacetime itself. The gravitational well deepens dramatically. The geometry changes. The universe adjusts. And in that adjustment, waves are born. These waves carry information about the mass, the spin, the formation process. They spread outward at light speed, thinning as they go, but never truly vanishing. Imagine that ripple traveling for millions or billions of years, crossing galaxies, passing through dust clouds, sliding through planetary systems, perhaps, one day, brushing gently through Earth. Black holes, despite their name, are not cosmic vacuums indiscriminately swallowing everything. If the Sun were magically replaced by a black hole of equal mass, Earth would continue orbiting as before. The gravitational pull at a distance would remain the same. What changes is the compactness, the steepness of curvature near the center. A black hole is extreme not because it devours everything, but because it concentrates mass into an extraordinarily small region. You rest with that nuance. It is geometry taken to its limit. The event horizon marks a boundary in spacetime, not in material substance. It is the edge of escape, the line where futures narrow. And yet, black holes are not static. They can spin. They can merge. They can interact. When two of them find each other in the vast darkness, drawn together by their mutual curvature, their dance will produce tremors far stronger than a single collapse ever could. But that is still to come. For now, you linger at the birth. At the quiet inevitability of gravity overcoming light. At the moment when a star's internal fire yields to curvature. A star lives by balance. A black hole forms when balance fails. And in that failure, spacetime bends more deeply than ever before. Somewhere in the dark, two such wells are beginning to sense each other's presence, their curved geometries overlapping, their paths slowly tightening, preparing for a dance that will make the universe tremble once again. You drift now into a darkness so complete that no light escapes it. There are no stars here, no glowing gas clouds, no radiant colors. Only curvature. Only gravity. Only two invisible presences moving in a slow, inevitable dance. Two black holes. They may have been born from massive stars that once shone brightly. Perhaps they formed together in a binary system, each star orbiting the other long before collapse. Or perhaps they met later, drawn together inside a dense star cluster where gravity weaves complex patterns. However they began, they are here now, bound to one another. You cannot see them directly. Their event horizons swallow light. But you can feel their influence. Each black hole carves a deep well in spacetime. And where those wells overlap, geometry grows complicated, dynamic, alive. Imagine again the stretched fabric. Place two heavy spheres upon it. Each creates its own depression. If they remain still, the fabric curves quietly around them. But now imagine they begin to move orbiting around a shared center. The fabric does not remain calm. It ripples. At first, the orbit is wide. The black holes circle each other slowly, perhaps taking hours or days to complete a single revolution. Their motion disturbs spacetime gently, sending faint gravitational waves outward in all directions. These waves carry energy. Energy must come from somewhere. And so, With each orbit, the system loses a tiny amount of orbital energy. The black holes draw slightly closer together. The circle tightens. You sense the rhythm increasing. Orbit by orbit, the distance shrinks. The speed grows faster. What once took hours now takes minutes. What took minutes now takes seconds. The dance becomes urgent, though still silent. Spacetime stretches in one direction and squeezes in another as each wave radiates away. If you could hover nearby, safely distant, of course you would not hear sound, but you would feel a steady oscillation. Stretch. Squeeze. Stretch. Squeeze. This is the heartbeat of merging gravity. The closer the black holes spiral, the stronger the waves become. The frequency increases. The amplitude grows. The trembling intensifies. You imagine the fabric beneath them now, no longer smooth but vibrating in complex patterns. The wells deepen as they approach. Their individual identities begin to blur in the curvature between them. This stage is called the inspiral. It can last millions or even billions of years, a long, patient narrowing. But in the final moments, time compresses. The last few orbits happen in a fraction of a second. The black holes are moving at a significant fraction of the speed of light, their paths whipping around each other in dizzying arcs. The gravitational waves now surge outward powerfully, carrying immense energy. In fact, during the final instant before merger, the power emitted as gravitational waves can briefly exceed the combined light output of all the stars in the observable universe. And yet, no light marks the event. Only curvature. Only trembling. Now the final approach. The event horizons draw near, their boundaries nearly touching. The fabric between them strains under extreme distortion. The geometry is no longer simple, no longer symmetrical. It twists and churns. Then they meet. The two horizons merge into one larger horizon. The separate wells become a single, deeper depression. The dance ends in union. This moment is called the merger. From outside, it is invisible in light. But spacetime itself reacts dramatically. A powerful burst of gravitational waves radiates outward, the strongest of the entire event. It is as though the fabric has been struck sharply, sending a clear, ringing pulse across the cosmos. You picture the stretched sheet again, suddenly snapped at its center. Waves ripple outward in expanding circles, crossing everything in their path. But even after the merger, the story does not end. The newly formed black hole is not immediately calm. It is distorted, shaped by the chaotic motion of the final embrace. It wobbles. It vibrates. It settles. This stage is known as the ring down. Like a bell struck by a hammer, the black hole emits gravitational waves at specific frequencies as it relaxes into a stable shape. These vibrations are not random. They depend on the black hole's mass and spin. The geometry itself determines the tone. Mass becomes music. Spin becomes pitch. The ringing fades gradually, the amplitude decreasing as energy radiates away. The black hole approaches equilibrium, smooth, symmetrical, quiet once more. And the waves continue traveling outward. Imagine them now crossing vast distances, passing through interstellar space. slipping through galaxies, expanding, thinning, but never stopping. For billions of years, they move. Eventually, some of these ripples may reach a small blue planet orbiting an ordinary star in a spiral galaxy. They pass through oceans, through mountains, through cities, through sleeping people who never feel them. Stretch, squeeze, stretch, squeeze. The distortions are unimaginably small by the time they arrive, altering lengths by less than the width of a proton. And yet, they carry a precise signature. Embedded in their frequency and amplitude is the story of the masses that merged, the speed of their orbit, the final spin of the new black hole. The waves are records. They are messages written not in light, but in geometry. You rest with the enormity of this. Two invisible objects collide in darkness. No photons escape. No glow announces the union. And yet the universe trembles so profoundly that the effect can be measured across unimaginable distances. The collision is both violent and elegant, destructive and creative. It erases two horizons and forms one. It releases energy in a form that barely interacts with matter, yet travels undisturbed across the cosmos. The fabric shivers and then grows calm. But calm does not mean silence. Somewhere, those waves are still traveling. Perhaps one is nearing Earth even now, carrying with it the imprint of a merger that happened before life arose on this planet. And if such a ripple passes through you, you will not notice. Unless, of course, you build something capable of listening. Unless you learn to measure distances smaller than atoms. Unless you find a way to turn the stretching and squeezing of space-time into a signal. Because the universe has already rung the bell. The question now is whether you can hear it. You return to the ripple. Not the collision now, not the black holes themselves, but the wave that leaves them behind. The quiet traveler. The invisible messenger. Gravitational waves are not made of particles in the way light is made of photons. They are not sound waves traveling through air. They are oscillations in space-time itself, the very fabric bending first one way, then the other. Stretch. Squeeze. Stretch. Squeeze. You imagine floating in open space as one passes. There is no wind. No vibration against your skin. No hum in your ears. Yet the distances between objects change ever so slightly. If 2 points are separated by a certain length, that length grows a fraction larger in one direction while shrinking in the perpendicular direction. Then it reverses. The effect is rhythmic and fleeting. The reason is simple, though it feels profound. A gravitational wave is not something moving through space-time like a ripple on water. It is a ripple of space-time. The medium and the motion are the same thing. This is why they are so difficult to imagine. You are accustomed to waves traveling through something, sound through air, water waves through oceans, light through electromagnetic fields. But here, the stage itself vibrates. And because space-time exists everywhere, the wave can travel anywhere. Unlike light, which can be absorbed or scattered by dust and gas, gravitational waves pass almost entirely unimpeded. Matter barely interacts with them. They slip through stars, through planets, through entire galaxies as though these objects are nearly transparent. This makes them extraordinarily pure messengers. The wave that reaches you today carries information from the moment it was born. It has not been distorted by clouds of dust. It has not been blocked by intervening matter. It arrives almost exactly as it left its source. Imagine a letter traveling across the cosmos, sealed and untouched, delivered billions of years after it was written. That is what a gravitational wave can be. You picture the merging black holes from the last chapter. Their spiral creates a rising tone. The frequency of the waves increases as the orbit tightens. This produces what scientists call a chirp. Not a sound in space, but a pattern that, when converted into audio, rises in pitch and intensity. It is the signature of a spiraling embrace. The shape of that chirp tells a story. The rate at which the frequency increases reveals how massive the black holes are. The amplitude, the strength of the stretching and squeezing, reveals how far away the event occurred. The final ringing frequency after merger tells you the mass and spin of the newly formed black hole. The wave is a fingerprint. You begin to sense how extraordinary this is. For centuries, astronomy depended on light. If something did not shine or reflect, it remained hidden. But gravitational waves allow you to perceive events that emit no light at all. Black hole mergers are the clearest example. They are dark by nature. Yet their collisions produce some of the most powerful gravitational wave signals in the universe. The cosmos has another language besides light. And you are learning its grammar. Consider the scale of these waves. When two stellar mass black holes merge, they may release energy equivalent to several suns converted entirely into gravitational radiation, all in a fraction of a second. This energy spreads outward in every direction, thinning as it expands. By the time it reaches Earth, the effect is tiny beyond comprehension. If you measure a distance of 4 kilometers, a passing wave might change the distance by less than 1,000th the diameter of a proton. You pause on that image. A proton is already unimaginably small. And the wave changes distances by a fraction of that. The universe trembles, and the trembling is almost imperceptible. Yet the pattern remains precise. Stretch in one direction while squeeze in another. Then reverse. The wave oscillates at a frequency determined by the source, perhaps tens or hundreds of cycles per second for stellar mass mergers. It is as if spacetime itself hums at a specific pitch. And these hums overlap. The universe is filled with countless gravitational waves from distant events. Most are too weak to detect individually. Together, they may form a background murmur, a gravitational wave background, the combined whisper of cosmic history. You imagine lying in a vast ocean at night. Individual ripples pass beneath you. Some are strong and distinct. Others are faint, blending into a gentle, continuous swell. This is the sea of spacetime. But here is the challenge. How do you measure something so small? How do you detect a change in length smaller than a proton across kilometers of distance? The answer requires extraordinary patience and precision. It requires isolating instruments from seismic vibrations, from passing trucks, from distant earthquakes. It requires lasers stable enough to measure shifts in distance smaller than atomic nuclei. You feel the delicacy of the task. The universe shouts in energy, but whispers in effect. To hear the whisper, you must quiet everything else. And so the question begins to form gently in your mind. If gravitational waves carry pristine messages across billions of years, if they encode the mass and motion of black holes, if they ripple through Earth unnoticed, can you build something sensitive enough to notice them? Can you transform stretch and squeeze into data? Can you turn geometry into sound? Because the waves are already here. They are already passing through the planet, through oceans and mountains and cities. They stretch the ground by imperceptible amounts and release it again. The universe has been ringing for billions of years. All that remains is to listen. And somewhere on Earth, in long, quiet tunnels arranged in perfect right angles, beams of light are already waiting to measure the trembling of space itself. You stand now on solid ground. After drifting through collapsing stars and merging black holes, you return to Earth, to deserts and forests, to concrete and steel. The sky above looks ordinary. Wind moves softly across the land. Nothing suggests that spacetime itself is trembling. And yet, hidden in quiet landscapes, enormous instruments wait. Imagine two long tunnels forming an L shape, each arm stretching 4 kilometers into the distance. At the corner sits a laser, steady, coherent, precise. The beam splits into 2 identical paths, traveling down each arm. At the ends, mirrors reflect the light back to the center, where the beams recombine. This arrangement is called an interferometer. Its purpose is simple in concept, though profound in execution. If both arms are exactly the same length, the returning light waves align perfectly. But if one arm becomes even slightly longer or shorter, the returning light shifts. The interference pattern changes. The device measures distance by comparing light to itself. Now imagine a gravitational wave passing through. As the wave moves across the detector, spacetime stretches in one direction while squeezing in the other. One arm of the L becomes slightly longer. The other becomes slightly shorter. A moment later, the effect reverses. Stretch. Squeeze. The change is unimaginably small, far smaller than the diameter of a proton. And yet, with enough care, enough isolation, enough repetition, the interferometer can detect it. You feel the delicacy of this effort. The Earth is not quiet. It trembles constantly. Tiny earthquakes ripple through the crust. Ocean waves crash against distant shores. Cars drive along highways. Even human footsteps create vibrations. To hear gravitational waves, scientists must quiet all of this. The mirrors hang from elaborate suspension systems that isolate them from ground motion. The tunnels are kept in high vacuum so air does not disturb the laser beams. Temperature fluctuations are carefully controlled. It is like trying to hear the faint flutter of a butterfly's wings during a storm. And yet, patience persists. For decades, researchers refined the instruments. They improve the stability of the lasers. They polish mirrors to extraordinary smoothness. They eliminate noise again and again. The project is called LIGO, the Laser Interferometer Gravitational Wave Observatory. 2 identical facilities are built in the United States, thousands of kilometers apart, one in Louisiana, one in Washington State. The separation ensures that any signal detected in both places at nearly the same time is not local noise, but something cosmic passing through Earth. You imagine the long beams of light waiting in darkness, reflecting back and forth between mirrors hundreds of times to increase sensitivity. the light itself becomes the ruler, measuring space with unwavering precision. Years pass without detection. The instruments listen. Silence. Upgrades are made. Sensitivity improves. The listening resumes. And then, on September 14, 2015, something changes. At both observatories, separated by thousands of kilometers, a signal appears. It lasts less than half a second. The pattern rises in frequency and amplitude, a clear chirp. The shape matches precisely what Einstein's equations predict for two black holes spiraling together and merging. Stretch. Squeeze. Stretch. Squeeze. The signal is analyzed carefully. Noise is ruled out. Independent teams confirm the pattern. Months of verification pass before the announcement is made. For the first time in history, humanity has directly detected gravitational waves. You pause there. A century earlier, Einstein predicted their existence. Many doubted they could ever be measured. And yet, here they are, not seen with eyes, but measured through light itself. The detected event came from two black holes about 1.3 billion light-years away. Each was more massive than the Sun. In their final moment of merger, they released energy equivalent to about 3 suns converted entirely into gravitational radiation. That energy crossed intergalactic space, traveled for over 1 billion years, passed through our planet and gently altered the length of LIGO's arms by less than 1,000th of a proton's width. And we heard it. You feel the quiet triumph in that. The universe had been ringing all along. The bell had been struck in distant darkness. And at last, we built an ear sensitive enough to notice. But listening does not end with a single detection. More signals follow. Additional mergers are recorded. Black holes of different masses, at different distances, each producing a distinct chirp. In 2017, detectors observed something new: the merger of two neutron stars. Unlike black holes, neutron-star collisions produce light as well as gravitational waves. For the first time, astronomers both hear and see the same event. A new era begins. This is gravitational wave astronomy. You imagine expanding the network. Additional detectors in Europe and Japan join the effort. Together, they can triangulate signals, determining where in the sky the waves originated. The universe becomes not only audible, but locatable. The instruments continue to improve. Sensitivity increases. The listening deepens. And yet, the principle remains beautifully simple. Light travels down two perpendicular paths. Spacetime stretches one and squeezes the other. The returning beams interfere slightly differently. A whisper becomes data. Data becomes understanding. You rest with the elegance of it. To measure the trembling of the universe, we use light, the very thing that once defined astronomy. But now light is not just a messenger from stars. It is a ruler measuring geometry itself. The earth remains noisy. The task remains delicate. But the success proves something profound: spacetime's ripples are real, and they can be heard. And now that you have heard the first chirp, the first ringing of merging black holes translated into signal, you may begin to wonder about the details hidden within that sound. Because after the collision, after the burst of energy, after the horizons merge, the new black hole does not fall silent immediately. It rings. And in that ringing, subtle patterns remain, patterns that reveal even more about the nature of gravity itself. You return now to that first signal. September 14, 2015. A quiet morning on Earth. No one feels anything unusual. No one looks up at the sky in alarm. And yet, deep within two long tunnels of light, spacetime trembles. The signal lasts less than half a second. At first, it is a low hum, a gentle oscillation. Then it rises in frequency, climbing quickly, like a tone sliding upward on a piano. The amplitude grows stronger. The chirp accelerates. And then, a peak. After that peak, something softer remains. This is the part you linger with now. The inspiral and merger are dramatic, but the aftermath, the ring down, is delicate and revealing. When the two black holes collide, they do not instantly become perfectly smooth and stable. The new black hole is distorted. Its shape is not yet symmetrical. Its geometry vibrates. Imagine striking a bell. The moment of impact is sharp and forceful, but the sound you hear afterward is shaped by the bell itself, by its size, its thickness, its material. The ringing tone carries information about the object that produced it. A black hole rings in much the same way. Of course, there is no sound in space. But the mathematics is similar. The newly formed black hole emits gravitational waves at specific frequencies determined by its mass and its spin. These frequencies are called quasi-normal modes, natural patterns of vibration that arise from the geometry of spacetime itself. You pause gently on that phrase. Natural patterns of vibration. The black hole does not choose how to ring. Its ringing is dictated by the curvature it creates. Mass sets the scale. Spin shapes the pattern. Nothing else matters. This is one of the most elegant predictions of general relativity, that a black hole is defined completely by only a few properties: mass, spin, and electric charge. In practice, charge is negligible for astrophysical black holes. So mass and spin remain. This idea is sometimes called the no-hair theorem. A black hole has no extra features, no hidden complexities visible from the outside. Once formed, it becomes simple. And its ring down reflects that simplicity. In the 2015 detection, scientists carefully analyzed the final portion of the signal. After the peak of merger, the waveform settled into a damped oscillation, a vibration that fades over time. By measuring the frequency and the rate at which it decayed, they could calculate the mass and spin of the new black hole. It was about 62 times the mass of the Sun. 3 solar masses had been converted directly into gravitational wave energy during the collision. You sit with that number. 3 suns, pure energy, radiated away in less than a second. And yet the Earth only felt a whisper. The ring down is short-lived. It fades quickly as energy dissipates. The black hole settles into a stable, rotating shape described by a solution to Einstein's equations known as the Kerr solution. It becomes smooth, quiet, dark. But in those final vibrations lies confirmation. If the frequencies had been wrong even slightly, it would have suggested something beyond general relativity. Perhaps a deviation from Einstein's predictions. Perhaps new physics. but the observed ring-down matched the theory remarkably well. The bell rang exactly as expected. And still, you feel the subtle tension in this moment. Because the ring-down is more than confirmation. It is a test. Each new merger provides another opportunity to compare observation with prediction. If someday the ringing differs, if an extra tone appears, or a frequency shifts, it could hint at new layers of reality. For now, though, the first ringing is clear and pure. You imagine the black hole settling, its event horizon smoothing into symmetry. The violent distortions of merger calm into rotation. The gravitational waves thin as they travel outward, their amplitude decreasing, their energy spreading across vast spheres of space. By the time they reach Earth, they are faint beyond comprehension. And yet they carry precision. The signal recorded by LIGO was not random noise. It was structured, predictable, elegant. The chirp of inspiral, the peak of merger, the fading oscillation of ring-down, all matching equations written a century earlier. You feel the quiet beauty of that. A theory born from thought experiments and mathematical insight finds confirmation in a ripple measured across kilometers of vacuum tunnels. The universe behaves consistently. And yet, you also sense how much remains unknown. The ring-down tells you about mass and spin. It confirms geometry. But what of the interior? What of the singularity predicted at the center? What of the interface between gravity and quantum mechanics? The ring-down cannot see inside the horizon. It only reveals the exterior shape. It is like listening to the tone of a bell without ever seeing the metal from which it is forged. Still, each ringing adds clarity. Each detection builds confidence. Scientists refine their models. They compare data with simulations. They search for subtle deviations. The black hole's final vibrations become not just a confirmation of theory, but a probe of its limits. And so you rest in that final fading note. Stretch. Squeeze. The oscillation weakens. The amplitude drops. The waveform flattens into quiet. The black hole is born anew, stable, spinning, dark. But the ringing lingers in the data, archived and studied, waiting for deeper interpretation. Because within those subtle oscillations may lie hints of physics beyond Einstein, clues that only reveal themselves when listening becomes even more precise. And so the question gently rises. What if, one day, the ringing is not exactly what we expect? You return once more to the ringing. Not to its drama, not to its energy, but to its precision. When a black hole settles after merger, its vibrations follow patterns that can be calculated. Long before detectors ever heard a gravitational wave, physicists solved Einstein's equations for rotating black holes. They derived the exact frequencies at which such objects should ring. It is as though the universe handed you a sheet of music before the orchestra ever played. Now, when a signal arrives, scientists compare what they hear to what the equations predict. They overlay waveform upon waveform, theory upon data, watching for harmony or for discord. So far, the harmony has been exquisite. The inspiral matches predictions. The merger aligns with simulations run on supercomputers. The ring-down frequencies fall exactly where general relativity says they should. But science does not rest in confirmation alone. It listens for deviation. You imagine a bell again. If it rings with a slightly unexpected overtone, a faint extra frequency, you would know something about its structure differs from what you assumed. Perhaps it contains a crack. Perhaps it is made from an unusual alloy. In the same way, if a black hole's ring-down includes extra modes or altered decay rates, it could hint that the structure of spacetime is not exactly as Einstein described. These natural frequencies, the quasi-normal modes, are determined by geometry. They depend only on mass and spin. If you measure one mode, you can predict the others. The relationship is strict, mathematical, elegant. This makes black holes perfect testing grounds. They are simple, at least from the outside. They strip away complications. No surface turbulence, no magnetic storms, no luminous atmospheres. Only curvature. When a merger occurs, the signal contains layers. The early and spiral tests how gravity behaves at relatively weaker curvature, when the black holes are still separated. The final plunge tests gravity under extreme conditions. The ring-down tests whether the resulting object behaves like the Kerr solution predicts. Each stage probes a different regime. You imagine holding the waveform like a seashell to your ear. Inside it are clues about spacetime under stress. But the challenge is subtle. Gravitational waves are faint. Noise from detectors must be carefully filtered. Statistical analysis becomes essential. Researchers compare many detections, stacking signals, searching for patterns that repeat. With each new event, confidence grows. Yet some physicists wonder whether tiny discrepancies may hide just below current sensitivity. Perhaps the event horizon is not perfectly smooth. Perhaps quantum effects near the horizon alter the ring down slightly. Some speculative theories predict faint echoes after the main ringing, delayed repetitions caused by new physics near the boundary. So far, no convincing evidence of such echoes has been confirmed. The data remain consistent with general relativity. But the search continues. You feel the beauty in this patience. Science does not rush to overthrow a theory. It tests, refines, questions, and tests again. Einstein's theory has passed every test for over a century, from the bending of starlight during eclipses to the precise timing of pulsars to the direct detection of gravitational waves. And yet, physicists know something incomplete remains. General relativity describes gravity as geometry. Quantum mechanics describes the behavior of particles and fields at the smallest scales. Both theories are astonishingly successful, but they do not yet fully reconcile with each other. Inside a black hole, at the singularity predicted by relativity, curvature becomes infinite. Quantum effects should become important. But current equations cannot describe that regime consistently. The ringing of black holes, therefore, becomes more than confirmation. It becomes a doorway. If any deviation from predicted quasi-normal modes were found, it could signal a bridge between relativity and quantum physics. It could reveal that the event horizon has subtle structure, or that spacetime behaves differently at extreme densities. You imagine listening to a vast cathedral bell in darkness, knowing that within its tone may lie the first hint of a deeper law. Each detection sharpens the ear. Detectors improve. Sensitivity increases. Future observatories will measure ring downs with greater clarity, isolating individual modes more precisely. Perhaps multiple tones will be resolved clearly enough to perform what physicists call black hole spectroscopy, analyzing the spectrum of vibrations just as astronomers analyze light spectra from stars. In spectroscopy, each element leaves a distinct pattern of lines. In black hole spectroscopy, each quasi-normal mode confirms the mass and spin relationship predicted by theory. If the tones align, Einstein stands firm. If they do not, something new waits to be understood. You feel the quiet tension of that possibility. The universe has already provided the ringing. It has given you the data. Now you refine your listening. Perhaps one day a signal will arrive slightly off-key, a frequency shifted, a decay time altered, a faint echo delayed beyond expectation. Would that mean spacetime is granular at the smallest scales? That the event horizon hides microscopic structure? That gravity merges with quantum uncertainty in ways not yet imagined? The waves do not shout these answers. They whisper. And you must learn to hear nuance within the whisper. For now, the tones match beautifully. The equations hold. General relativity stands resilient. But science remains open. Because every ringing is both confirmation and invitation. And as detectors grow more sensitive, as signals accumulate, as the cosmic symphony becomes clearer, you begin to sense that black holes are not only testing Einstein's vision, they may also be pointing gently beyond it. You linger with the sound of spacetime vibrating. The ringing of black holes is more than mathematics made audible. It is a map, a subtle tracing of geometry that stretches across vast distances, a history of violent, unseen events. And yet, beneath the elegance lies a mystery deeper than any individual signal. Consider what lies beyond the event horizon. According to general relativity, the interior is a singularity, a point where density becomes infinite and our known laws of physics collapse. Yet quantum mechanics tells you that infinities do not exist in nature. Something must reconcile the two. Here, at the edge of a black hole, the universe whispers of unknown rules. You imagine the horizon itself not as a smooth, featureless boundary, but as a dynamic surface. Some theories suggest it could host structures too small for classical physics to detect, tiny fluctuations, like ripples on a pond too small for the eye to see. Others propose firewalls, energetic layers that incinerate anything approaching too closely. Still others hint at the horizon as a holographic screen, encoding all information about the matter that formed the black hole, a two-dimensional projection of a three-dimensional interior. Each idea is bold, speculative, yet mathematically grounded. Each challenges your understanding of reality. The ringing of black holes may carry faint clues. Tiny deviations in the decay of quasi-normal modes, or subtle echoes following the ring down, could reveal hints of quantum gravity, a bridge between the smooth curves of relativity and the jittery uncertainty of the quantum world. You feel the tension of these two realms. Relativity excels at explaining large-scale structure, stars, galaxies, the curvature of the cosmos itself. Quantum mechanics governs the tiniest constituents of matter, electrons, quarks, fields that fluctuate even in empty space. And yet, in black holes, these two regimes converge. The very small interacts with the very large. Gravity and quantum mechanics dance where no other celestial object can bring them together. It is as if a laboratory has been set up, billions of light years away, and you are listening through spacetime itself. Each merger, each ring down, each traveling ripple is an experiment conducted without human intervention, obeying the fundamental laws of nature. And the universe provides its results in whispers. You begin to sense the layers of information embedded in the ringing. The frequency and decay rate of the quasi-normal modes reveal the mass and spin. Tiny anomalies could hint at new physics. Delayed secondary echoes, if detected, might expose microscopic structure at the horizon, subtle hints of the quantum world interfering with classical predictions. Imagine that, a vibration, billions of years old, traveling silently, reaching Earth, and speaking to humanity about the fundamental building blocks of reality. It is humbling. You consider what these signals might teach. Perhaps black holes are not merely endpoints of stellar evolution, but laboratories for unifying physics. Perhaps they are messages from the cosmos, waiting for ears sensitive enough to interpret them. Perhaps the universe has left a record of its deepest laws hidden in waves that stretch across galaxies. And yet, the ringing does not give easy answers. It is subtle, quiet, deliberate. The clues lie in slight deviations, in the timing of the decay, in the faintest echoes that might follow the primary signal. Detecting these requires extraordinary precision. Instruments like LIGO and Virgo, detectors in multiple locations to isolate noise, years of careful observation, and patient analysis. You feel the patience that science demands. It is a patience that stretches across decades. That counts small changes in length smaller than a proton. That waits for cosmic events that occur once per millennium in any given galaxy. That trusts the mathematics, even when the answers are slow to arrive. And in that patience, wonder unfolds. Because the ringing is not just a signal of a merger. It is an invitation to explore the unknown, to question what lies beyond the classical horizon, to imagine the fabric of spacetime vibrating not only with gravity but perhaps with the signature of quantum effects. You picture a black hole merger sending waves outward, billions of years in transit, eventually brushing past Earth. You imagine a detector in a quiet valley, recording the tiny oscillations of spacetime. You imagine researchers analyzing the data, filtering out every source of noise, seeking patterns within the faintest traces. And you understand that the unknown is encoded in these patterns. The ringing becomes not merely a confirmation of Einstein, but a probe. Each oscillation, each fading tone, becomes a test. If all matches theory, relativity holds firm. If deviations appear, a new doorway opens. Perhaps it leads toward a theory of quantum gravity. Perhaps it hints at the microscopic structure of horizons. Perhaps it reshapes your understanding of space and time entirely. Even more, you realize that the black hole is not a distant curiosity. It is a part of the same universe you inhabit. Its echoes ripple through the same spacetime that supports your body, your thoughts, your very perception of distance and duration. The cosmos is not separate, you are woven into the same fabric. The act of listening itself becomes meditative. You focus on each stretch and squeeze of spacetime, aware that the tiniest vibrations may carry monumental truths. You realize that knowledge of the universe is built on sensitivity, patience, and reverence for subtlety. And with that awareness comes a quiet thrill. The universe has been ringing long before you existed, long before any human could measure it. Its signals traverse galaxies, brushing past stars and planets, carrying messages that are only now being understood. You feel the echo of billions of years, faint but persistent, and it resonates within your mind. The black holes, once isolated and invisible, have become teachers. Their collisions demonstrate extreme gravity. Their ring-downs test your theories. Their whispers challenge your imagination. They reveal that even in darkness, there is structure, order, and communication. And perhaps most profoundly, you feel the openness of the cosmos. Despite all we have learned, despite all we can measure, much remains mysterious. The ringing does not answer every question. It leaves space for wonder, for hypothesis, for the continual unfolding of discovery. You imagine the next wave arriving, carrying hints you have not yet predicted. You sense the possibility that the fabric of reality may hide surprises and frequencies so faint that only the most sensitive instruments can detect them. And in this anticipation, science feels both intimate and infinite, a quiet conversation with the universe itself. Because the ringing is more than sound. It is information. It is a question. It is a bridge between what is known and what is yet to be discovered. And as you focus on the last fading tones, you understand that the cosmos has more to teach, not through light alone, but through the tremor of spacetime, the echo of a collision, the resonance of the unknown, waiting patiently to be heard. You step into a new perspective, one that merges sight with sound, observation with listening. For centuries, astronomy relied on light. You looked through telescopes at stars, nebulae, galaxies, and planets. You mapped their positions. You recorded their brightness. You interpreted their colors. The cosmos communicated in photons, and your instruments translated that language. But now, gravitational waves offer another dimension. The universe does not only shine, it trembles. The vibrations carry information that light alone cannot reveal. You are no longer limited to the luminous events. You can hear collisions that emit no photons at all. You can perceive black holes merging in the darkness, neutron stars spiraling together, even cosmic collisions that were previously invisible to every telescope ever built. You imagine two neutron stars, dense remnants of massive stars, orbiting each other in a cosmic embrace. Each is about the size of a city, yet their mass exceeds that of the sun. They circle ever closer, their motion sending ripples through space-time. Unlike black holes, these objects can produce light when they collide. Gamma-ray bursts flare, kilonovae explode with radiant energy. For the first time, you both see and hear a cosmic event. Light illuminates the spectacle, gravitational waves reveal the motion, mass, and dynamics of the merger. This dual observation transforms your understanding. The universe is no longer a painting observed from afar, it is a symphony experienced. Each cosmic event produces multiple channels of information, and together they paint a richer picture of reality. You feel the intimacy of the experience. You are not merely a distant observer. You are attuned to the universe's vibrations, aware of its rhythm, capable of perceiving events billions of light-years away. Gravitational wave astronomy expands further. Detectors improve. Observatories across the globe collaborate. Triangulation allows you to pinpoint the location of mergers with surprising precision. You imagine a network of instruments in North America, Europe, and Asia, their lasers crisscrossing tunnels, their mirrors vibrating imperceptibly. Each instrument contributes to a global ear, a collective sensitivity that enhances the clarity of the cosmic song. The first detection of a neutron-star merger confirmed that these events forge heavy elements. Gold, platinum, and other rare materials are produced in the cataclysmic explosion. You feel the connection between distant astrophysical phenomena and the very matter that makes up your world. Every shimmer of gold you see, every platinum ring, is a trace of a collision that occurred millions or billions of years ago, its gravitational waves still reverberating through space, possibly reaching Earth even now. You notice how this mode of astronomy reshapes cosmic history. Events that were invisible in light can now be heard. Black hole mergers inform the population of compact objects in galaxies. Neutron-star collisions reveal the production of heavy elements and the physics of extreme matter. Gravitational waves allow you to probe the expansion of the universe, the behavior of gravity under extreme conditions, and the evolution of massive stars. Listening changes your perception. You no longer consider the universe only as a visual tapestry. You now perceive its dynamics, its energy flows, its hidden choreography. The cosmos has depth not only in space but in the dimension of vibration. You hear its heartbeat. You feel its pulse. The signals are still faint. They require patience, careful analysis, and long-term observation. But as detections accumulate, patterns emerge. You begin to perceive the demographics of black holes, their masses, spins, and frequencies of merger. You begin to see the variety of neutron stars, their mass distribution, how often they collide, the speed of their rotation. You even glimpse potential intermediate mass black holes, mysterious objects that bridge the gap between stellar remnants and supermassive black holes. With each detection, your knowledge of the cosmos grows. Gravitational wave astronomy complements traditional methods. Photons tell you the location, color, and brightness. Waves tell you motion, mass, and geometry. Together, they form a richer, multidimensional understanding. The universe can now be felt as well as seen. You imagine the future. Detectors in space, like the planned LISA observatory, will measure even longer wavelengths. They will capture the slow dance of supermassive black holes orbiting each other in distant galaxies. You will hear events occurring millions of years before Earth even existed. The cosmic symphony stretches across time and space, and you are learning to interpret it. And you feel a quiet exhilaration. Astronomy is no longer only about looking. It is about perceiving, listening, feeling the universe. Every collision, every ring down, every ripple is a message, a new note in a score that has been playing since the dawn of cosmic time. You consider the intimacy of this form of observation. A signal arrives, subtle and fleeting. Scientists measure it, analyze it, and interpret its meaning. You realize that humanity has extended its senses beyond the traditional. You are now attuned to spacetime itself. You have transformed the imperceptible into the understood. You rest in the awareness of this new vision. You sense that astronomy has entered a different era, one where observation and perception are intertwined, where the cosmos can be experienced in both sound and sight. You are not just seeing history, you are hearing it, feeling it, connecting with it in a way that transcends ordinary perception. And in that moment, the universe continues to ring, wave after wave, collision after collision, carrying not only the echoes of massive objects but also the whispers of secrets yet to be understood. You listen, and in listening, you see in an entirely new way. You step into the quiet anticipation of tomorrow. The first detections on Earth were monumental. They transformed your understanding of the universe, revealing that spacetime itself can ripple, and that the cosmos has been humming across billions of years, waiting for someone to listen. But these are only the earliest notes of an ongoing symphony. What if you could move beyond the confines of our planet, beyond the disturbances of earthly vibration, beyond the limitations of kilometer-scale interferometers? Imagine instruments floating in space, isolated from the clamor of seismic tremors, free from winds, traffic, and oceans. Solar orbit allows detectors to drift quietly, maintaining perfect stability over millions of kilometers. Laser beams traverse vast distances between satellites, measuring tiny stretches and compressions in spacetime with unparalleled precision. You sense the elegance of this cosmic stage. Earth-bound detectors hear local ripples, space-based observatories listen to the universe itself, nearly undisturbed. One such planned observatory is LISA, the Laser Interferometer Space Antenna. 3 satellites form an immense triangle, each arm millions of kilometers long, drifting through the solar system in a slow, coordinated orbit around the Sun. The distance between spacecraft is measured with lasers, capable of detecting distortions smaller than a proton. This network will be tuned to lower frequency waves, the deep hums of supermassive black holes, and the gentle orbiting of binaries too slow for terrestrial detectors to capture. You feel the vastness of it. In space, you can hear events that occurred eons ago, stretching across time in waves that have traveled billions of light years. The universe becomes a library of vibrations, each merger, collision, and orbit adding pages to an ever-growing catalog. Black holes of every mass, neutron stars spiraling in intimate dances, even the subtle murmur of primordial ripples left over from the earliest moments of the cosmos all become accessible through patient listening. You imagine the expanding catalog. Each entry is a voice from a distant epoch, a record of a cosmic event that once occurred long before Earth existed. Some signals are bold, immediate, and powerful. Others are faint, stretched across space, arriving gently after traversing unimaginable distances. Together, they create a chorus of spacetime, each contributing a note to the symphony of the universe. And yet, for all this listening, you realize we are still at the beginning. Earth-based detectors have captured only a handful of mergers. Space-based observatories remain in preparation. The faintest signals, those from the earliest epochs of cosmic history, are still beyond our reach. Gravitational waves travel unimpeded, yet detecting them requires not only sensitivity but also patience, stability, and ingenuity. You reflect on the implications. By listening further and deeper, you may perceive black holes forming in the first galaxies, the earliest neutron star collisions, or even the residual hum from inflation, a whisper from the birth of the universe itself. Each detection is a window into the past, allowing you to map the evolution of cosmic structure and witness the growth of stars, galaxies, and black holes across billions of years. You feel the intimacy of this endeavor. The universe is vast and ancient, yet through the careful listening of gravitational waves, it becomes tangible. Each signal is a connection, an echo of events so distant and extreme that they would otherwise remain forever invisible. And in this connection, you sense your own place in the cosmos. The waves pass through the earth, through your body, through every structure that has mass, linking you subtly to events that occurred long before your time. The quiet future of cosmic listening promises more than discovery, it promises a shift in perspective. For the first time, you are not limited to observing the light of the universe. You are attuned to its motion, its rhythm, its very geometry. You perceive collisions and mergers not only as mathematical events but as physical experiences, subtle shifts in the fabric of reality itself. Consider the possibilities. Future detectors may triangulate with exquisite precision, pinpointing sources across the sky with accuracy that rivals traditional astronomy. Multi-messenger astronomy will combine gravitational waves with light, neutrinos, and cosmic rays. You will both see and hear, touch and interpret the intricate dance of matter and energy in ways previously unimaginable. The universe will no longer be silent to the patient and perceptive ear. And yet, even with such sensitivity, much remains beyond reach. The background hum of countless unresolved events creates a gravitational wave symphony, a gentle murmur threading through space. Primordial signals from the early universe may lie beneath that murmur, subtle and elusive, waiting for instruments tuned with unprecedented care. Each improvement, each new observatory, brings you closer to deciphering the message. You feel the scale of this patient endeavor. Scientists and engineers work for decades, refining lasers, mirrors, and orbital mechanics. And in that patience, wonder thrives. You sense the universe continuing its ceaseless rhythm, sending ripples through the cosmos, each a story of gravity and motion, of stars born and dying, of collisions that shape galaxies, of black holes settling into silent symmetry. These stories existed long before you, before life on Earth, before your planet coalesced from cosmic dust. And they will continue long after, flowing through space like a river without end. You realize that humanity is only just beginning to listen. Earth-based detectors have opened the first window. Space-based observatories will open a second, wider, more profound one. Together, they form the foundation for centuries of observation, a gradual, attentive mapping of the gravitational symphony that fills the cosmos. The catalog of black hole voices grows steadily. Each new detection is a chapter in the ongoing story of the universe. You imagine future generations listening to events that occurred billions of years ago, interpreting the faint oscillations that travel through spacetime, understanding the physics of objects that are both near and unimaginably far. And you sense the continuity of it all. The universe hums, its vibrations eternal. Your instruments, your analysis, your understanding, all are temporary. Yet in this temporary act of listening, you connect with something timeless, a cosmic rhythm that endures across space and time. You rest in the awareness of this ongoing conversation. The universe continues humming, quietly, persistently, infinitely, beyond any one detector, any one observation. And even as you learn, even as instruments grow more precise, there is always more to hear, more to understand, more to imagine. Because the universe has been whispering for billions of years, and your patient listening is only beginning. Stretch. Squeeze. Stretch. The faint hum continues, carrying secrets you are not yet ready to fully grasp, but will, in time, learn to interpret. You lie back beneath the familiar night sky once more, the air cool against your skin, the stars silent witnesses to epics of cosmic drama. After drifting through ripples of spacetime, witnessing black holes dance, collide, and settle, you return to this moment of quiet reflection. The earth beneath you feels solid, stable, ordinary, but you know differently now. Every particle, every atom, every corner of this planet rests within the gentle curvature of spacetime, subtly influenced by gravity's omnipresent embrace. The echoes of distant mergers, billions of light-years away, have passed through this very space. They have traveled across vast emptiness, brushing past galaxies, threading through the cosmic web, and finally, reaching your instruments, your awareness, your imagination. Each vibration carries a history older than civilization, older than life on Earth, older than the sun itself. You sense a connection, subtle yet profound. The universe's events are intertwined with your own existence, the quiet tremors of spacetime passing through you even now. You consider the journey that has brought you here. You have imagined the collapse of massive stars, the spiraling union of black holes, the subtle vibrations of ring-downs, the patient listening of LIGO, Virgo, and future space-based detectors. You have understood that each ripple is more than a signal, it is a story, a record of geometry, energy, and motion, a question posed to those patient enough to listen. And in that story, you sense your own reflection. The curvature of spacetime underlies the rhythm of your heartbeat. The force of gravity binds your body, your planet, and your solar system. Even the light that illuminates your world bends slightly as it travels, tracing paths influenced by unseen mass. The universe is not separate from you, you are woven into its fabric, a participant in its endless motion. You breathe slowly, allowing this connection to deepen. You feel a rhythm in the silence, a faint resonance that echoes the cosmic symphony you have imagined. The ringing of black holes, once distant and abstract, now feels intimate. It is a reminder that the universe has always communicated, not only through photons but through the very structure of space and time. And although most of these vibrations are imperceptible, humanity has learned, at last, to extend its senses and receive them. You reflect on the lessons these echoes offer. They have taught you patience and attentiveness, the importance of careful measurement, and the elegance of natural law. They have shown you that even the most violent events, mergers releasing energy equivalent to multiple suns, stars collapsing into singularities, are governed by predictable, comprehensible rules. And they have whispered of mysteries that remain, of horizons that hide singularities, of possible quantum effects beyond your current understanding. Yet now, after so many journeys into distant space and time, a different sensation emerges. It is the quietness after the ringing, the final fading note that marks the boundary between sound and silence. You realize that science, like the universe, is a rhythm, an alternation of discovery and reflection, of observation and pause. Each wave carries knowledge, and each pause allows it to resonate, to settle, and to integrate into understanding. You notice how this rhythm mirrors life itself. There is motion and rest, stimulus and reflection, curiosity and contemplation. Listening to the universe is not merely about acquiring facts, it is about attuning to the patterns of reality, understanding your place within them, and finding calm within the vastness. You sense that this practice of attention, of attuning yourself to subtle vibrations, whether in space or within your own mind, is a form of meditation, a bridge between intellect and awareness. As you lie under the stars, you imagine the future. New instruments will drift in space, detecting fainter and older waves, reaching back to the earliest epochs of the cosmos. Detectors on Earth will continue to improve, capturing more mergers, more ring-downs, more intricate whispers. One day, perhaps, you will hear the remnants of the first black holes that formed, the echoes of collisions before galaxies had settled, the tremors of spacetime from the birth of the universe itself. Even now, you recognize that these signals are continuous. The universe has never stopped ringing. It only becomes perceptible as your instruments and understanding become sensitive enough to detect it. Each generation of observers adds clarity to this ongoing symphony, translating vibrations into insight, and insight into knowledge. And in this continuum, you perceive both your own temporality and your place within a vast, persistent flow. You draw your attention inward. The universe's ripples pass through your body, imperceptibly stretching and squeezing the space around you. Your own existence is enmeshed in these vibrations. Gravity, after all, acts everywhere, shaping the very geometry that supports your life. You sense that listening to cosmic echoes is not an act of separation from the universe, but a recognition of intimate connectivity, that you, too, are part of the fabric that ripples, that bends, that stretches and calms in the same rhythm that shapes galaxies and stars. The ringing fades gradually, like the last vibration of a bell settling into silence. And yet, silence in this context is not emptiness. It is a space of potential, a quiet that holds memory and possibility. It allows reflection, insight, and the imagining of what is yet to be heard. The universe rests in a moment of calm, but its symphony is ongoing. Even as one event passes, another begins, somewhere beyond observation, beyond current reach, beyond the span of human perception. You feel gratitude for the ears you have developed, both literal and metaphorical, for the patient mind and attentive body that have carried you through the journey. You sense the enormity of what has been discovered and the humility of what remains unknown. Each gravitational wave, each ring down, each faint echo is a reminder that learning is endless, and that even the vast and ancient universe still has secrets to whisper. In this stillness, under the vast night sky, you recognize a rhythm between listening and silence, between the known and the unknown, between the fleeting vibration and the infinite quiet. The universe continues, humming softly, inviting your awareness. And you rest within this gentle cadence, part of a cosmic meditation that stretches across time and space, reaching both outward into the cosmos and inward into your own consciousness. And as the last traces of ringing fade from your mind, a deeper silence settles, not empty, but full of potential, of questions yet to be asked, of vibrations yet to arrive, of discoveries still waiting beyond the horizon. Stretch. Squeeze. The universe continues to whisper, and you remain attuned, listening gently for the next note.